Long before mechanical clocks ticked and digital displays illuminated our nights, humans observed the world in search of order. The rising and setting of the sun, the waxing and waning of the moon, and the slow dance of the stars across the heavens were the earliest markers of the passage of time. People understood, intuitively, that life moved in cycles. The planting and harvesting of crops depended on the seasons, religious rituals aligned with celestial events, and daily activities followed rhythms dictated by the sun. Time, in its first human form, was a living, breathing concept, one intimately tied to nature and the cosmos. Sunrise and sunset were more than simple markers of day and night. They framed human existence, providing structure in societies that had no mechanical clocks, no printed calendars, and no standardized hours. Early communities observed how the length of daylight changed with the seasons, noting the first day of longer days as the promise of summer warmth and the gradual encroachment of darkness as winter approached. Farmers learned to read the sun's height and the shifting stars to guide planting cycles. Priests and shamans interpreted these changes as omens or signs, linking the celestial to the terrestrial. Even the tides, governed by the moon's gravity, became vital in coastal communities, influencing fishing, travel, and ritual. In Mesopotamia and Egypt, the human desire to measure time concretized into the earliest devices. Sundials appeared as simple yet sophisticated tools, casting shadows that shifted across marked surfaces to indicate hours. In Egypt, priests used shadow clocks, or gnomons, to mark the time for ritual offerings, aligning their practices with the movements of the sun. Microstory. Imagine an Egyptian priest around 1500 BCE, stepping into the courtyard before dawn. He adjusts the shadow clock, watching as the sun slowly illuminates the markings etched into the stone. As the first light touches the courtyard, he signals the beginning of morning prayers. Each day repeats this precise choreography, demonstrating an early mastery of observation, measurement, and ceremony. Water clocks, or clepsydras, offered another approach. In Egypt, Babylon, and later China, water was measured as it dripped from one vessel to another, marking the passage of hours and guiding judicial, governmental, and ritual functions. Unlike sundials, which required sunlight, water clocks worked at night or indoors, allowing societies to measure time continuously. A Babylonian judge might consult a clepsydra to regulate court sessions, while Chinese astronomers monitored water flow to time festivals and celestial observations. Microstory. Picture a Chinese astronomer in the Han Dynasty carefully observing a water clock before a lunar festival. He notes the exact moment the final drop falls, signaling the start of rituals that unite the village under the same rhythm. Precision here was not just practical. It connected the human community to a shared temporal experience. In East Asia, candle and incense clocks added artistry and symbolism to the measurement of time. Candles marked hours as they burned, often carved with notches or markings, while incense coils released fragrant smoke at regular intervals. These devices served multiple purposes, signaling prayer times, timing ceremonies, and reminding the living of the passage of life. The ephemeral nature of burning wax or incense mirrored the fleeting nature of human existence, offering not only utility but reflection. People witnessed time's passage as both a practical necessity and a philosophical meditation. Early societies understood that coordinating human activity with cosmic rhythms required not only tools but social structures. Timekeeping became a shared endeavor. Agricultural work, religious ceremonies, and social gatherings all depended on synchrony. Communities learned to rely on these devices, fostering trust in human ingenuity and collective observation. Reflections on mortality intertwined with this practical knowledge. Seeing shadows lengthen across a sundial reminded humans of the impermanence of a day, a season, and a life. The cycles of sun and moon became metaphors for continuity, change, and the eternal rhythms of the universe. Cultural exchange amplified these innovations. Trade routes carried sundial designs from Egypt to Greece, water clock techniques from Babylon to Persia, and incense clock traditions across East Asia. Scholars and artisans adapted, refined, and combined methods, producing diverse systems that reflected both local needs and shared human curiosity. Microstory. A merchant traveling the Silk Road carries knowledge of Egyptian shadow clocks to a Greek city. There, local artisans experiment with materials and angles, merging new ideas with traditional practices. Communities across continents begin to experience time in ways previously confined to temples, observatories, or royal courts. Through these early inventions, humans developed a profound awareness of rhythm, structure, and predictability. Observation turned into measurement, measurement into planning, and planning into culture. Festivals could be held on precise days, markets opened at coordinated hours, and work cycles became predictable. Knowledge of time became intertwined with governance, religion, and social cohesion, illustrating that the measurement of time was as much a social innovation as it was a technical one. These early timekeeping efforts were not without experimentation and error. Sundials had to be adjusted for latitude, water clocks required careful calibration, and candle clocks demanded attentive observation. Each innovation taught its users about patience, precision, and the consequences of miscalculation. The process itself, repeated observation, refinement, and replication, mirrored the larger scientific method, centuries before it was formally codified. Human ingenuity was both practical and philosophical, demonstrating an evolving understanding of how to harmonize life with the cosmos. The integration of timekeeping into everyday life fostered reflection on human mortality and the universe's vast scale. Observing the predictable motion of celestial bodies prompted questions. What is the human place within these cycles? How can societies synchronize their fleeting lives with the immense, slow movements of stars and planets? Priests, astronomers, and scholars across cultures pondered these questions, connecting the practical act of measuring time with existential reflection. Human ingenuity was never divorced from the larger quest to understand the world. Trade and cultural interactions ensured that these lessons were not isolated. Knowledge of sundials, water clocks, and incense clocks traveled across continents, inspiring new applications. Techniques adapted to local climates, materials, and social structures, creating a tapestry of timekeeping traditions. Scholars shared methods during diplomatic missions, artisans passed on construction techniques, and merchants carried stories of innovative devices. This cross-pollination underscores a central theme. The pursuit of measuring time was simultaneously universal and deeply human, bridging geography, culture, and centuries. Microstory. In Mesopotamia, a scribe records the movement of the sun on a newly designed sundial, consulting previous texts brought from Egypt. He notes that the shadow shifts slightly differently due to local latitude, adjusts the markings, and presents the improved sundial to the city council. Villagers use it to regulate work hours and temple rituals. Across the desert, a caravan merchant observes a similar device and is inspired to commission a water clock for his trading post. Time, once abstract, begins to unify human activity in unprecedented ways. By the time civilizations reached classical antiquity, timekeeping had become both precise and symbolic. Sundials adorned public spaces in Athens and Rome, guiding civic life. Water clocks measured court proceedings and inspired early theories of hydraulics. In China, incense clocks signaled meditation and ritual. Across continents, humans had discovered that the act of measuring time itself reshaped behavior, reinforced societal cohesion, and offered insight into the cosmos. The natural rhythms observed by ancient humans, sunrise, moon phases, tides, remained foundational. Every device built was an attempt to capture these rhythms, to make them comprehensible, measurable, and shareable. Through ingenuity, societies translated the invisible passage of time into physical forms: shadows, dripping water, burning candles, and fragrant incense. Each method carried meaning beyond utility, linking humans to the universe's larger patterns. Even today, we carry the legacy of these innovations. Modern clocks, calendars, and atomic timing systems all owe their conceptual lineage to the careful observation of shadows, flowing water, and celestial movements. The Egyptian priest adjusting a sundial, the Chinese astronomer timing a festival, and the Mesopotamian scribe refining a shadow clock. All are part of a continuum that has allowed humanity to measure, coordinate, and reflect on time. Timekeeping, in its earliest form, was a quiet dance between humans and the universe. It required patience, observation, and creativity. It demanded that societies synchronize their lives, align their work and rituals, and contemplate the greater cosmos. It was both practical and philosophical, a blend of ingenuity, culture, and reflection that shaped civilizations and the human experience. Long before clocks ticked or digital displays illuminated our nights, humans wrestled with a deeper question than marking hours: how to organize the days, months, and years that define the rhythm of life. While sundials and water clocks measured hours, civilizations soon realized that the true challenge lay in understanding longer cycles: the waxing and waning of the moon, the orbit of the Earth around the sun, and the apparent movement of stars and planets. Agriculture, religious rituals, political governance, and trade all depended on accurate long-term timekeeping. Humans, ever curious and meticulous, began translating the invisible passage of time into structured calendars. In ancient Mesopotamia, the Babylonian civilization led one of the earliest formal attempts to create a lunar calendar. The Babylonians observed the moon's phases carefully, noting how the crescent's appearance marked the passage of a month. Microstory. Imagine a Babylonian priest in 600 BCE, gazing at the night sky with keen eyes and meticulous notes. A solar eclipse approaches, its shadow sweeping across the land. He records the phenomenon, noting its timing against the lunar month, and adds annotations to clay tablets destined for future generations. His work will guide not only agricultural cycles but also religious festivals and state ceremonies, ensuring the community maintains harmony with the cosmos. The Babylonian calendar structure, though simple compared to later systems, demonstrated an extraordinary understanding of celestial mechanics and human necessity. Meanwhile, in Egypt, the solar calendar emerged as a tool for agriculture and societal planning. Farmers depended on the annual flooding of the Nile to enrich fields with fertile silt. Predicting the inundation was a matter of life and survival, so Egyptian priests devised a calendar based on the sun's position and the heliacal rising of Sirius. This solar calendar divided the year into 12 months, each consisting of 30 days, with 5 extra days to align with the solar year. Microstory. A farmer in Thebes consults the temple's calendar to determine when to begin sowing wheat. He trusts not only the observations of the priests but also the collective knowledge accumulated over generations. The sun and stars dictate his labor, demonstrating how calendars were woven into the very fabric of daily life. Far to the east, Chinese civilizations developed a lunisolar calendar, balancing lunar months with solar years to guide both agricultural and ceremonial events. Each month began with a new moon, but adjustments were necessary to prevent seasonal drift. Intercalary months were added when necessary, ensuring that the calendar remained synchronized with planting and harvest cycles. Microstory. In a Han Dynasty village, an astronomer meticulously observes the moon's phases and planetary positions, adjusting the calendar for the coming year. Festivals, market fairs, and rituals are scheduled according to these observations, reinforcing the interconnectedness of community life and celestial order. The precision and adaptability of the Chinese lunisolar calendar highlight a sophisticated understanding of both astronomy and social coordination. Across the Atlantic, the Maya of Mesoamerica developed one of the most remarkable calendrical systems in human history. The Mayan calendar combined ritual, civil, and astronomical cycles into a complex framework that guided everything from agriculture to ceremonial life. The long count calendar allowed Mayan astronomers to track centuries with remarkable accuracy. Microstory: a Mayan astronomer, chiseling glyphs into a ceremonial calendar stone for the city's rulers, calculates the precise day for planting maize. His work ensures the prosperity of the community, aligning earthly labor with celestial rhythms. The accuracy of the Mayan calendar astonished later civilizations and remains a testament to human ingenuity in timekeeping. Calendars were never just practical tools. They were instruments of political and religious power. In Babylon, priests controlled the timing of festivals, eclipses, and ceremonies, influencing state decisions and public life. In Egypt, pharaohs relied on precise calendars to organize taxation, labor for monumental construction, and religious events. Microstory: in Rome, civic officials adjust the calendar to align with political priorities, ensuring that religious observances coincide with public events and military campaigns. The authority to measure time was intertwined with governance, reinforcing the societal importance of accurate calendars. Adjustments like leap years, intercalary months, or occasional corrections to reconcile lunar and solar cycles reveal the deep awareness of ancient societies about the imperfections of time measurement. These interventions were not merely technical. They carried profound cultural and philosophical implications. Civilizations interpreted irregularities, eclipses, anomalous tides, or unexpected weather as omens or messages from the divine. Rituals were often scheduled to align with celestial anomalies, embedding cosmic observation into the moral and spiritual life of the community. Cross-cultural exchange played a pivotal role in advancing calendrical knowledge. Traders, diplomats, and scholars carried ideas across continents, allowing innovations to spread and evolve. Microstory: a merchant traveling the Silk Road shares a Babylonian calendar system with Chinese astronomers. They adapt the system to incorporate lunar and solar cycles, creating new calculations for intercalary months and festival dates. Knowledge becomes a living entity, traveling with people and reshaping societies wherever it arrives. The integration of timekeeping into human society also fostered reflection on mortality, destiny, and the passage of civilizations. Civilizations recorded astronomical phenomena not only for practical purposes but as markers of historical continuity. Tablets, inscriptions, and monuments documented eclipses, solstices, and planetary alignments, creating records that allowed future generations to connect with the past. Microstory: a scribe in Maya city-states records the positions of Venus and Mars alongside ceremonial dates, ensuring that the patterns of the heavens are remembered centuries later. This practice illustrates how calendars were a bridge between ephemeral human life and enduring cosmic cycles. Through calendars, humans developed a shared temporal framework that shaped social cohesion. Festivals, harvests, trade fairs, and religious observances were coordinated through collective understanding of time. Calendars allowed communities to plan labor, commerce, and celebration with unprecedented accuracy. They became instruments of education and moral instruction, teaching successive generations to recognize patterns, anticipate changes, and act with foresight. In medieval Europe, the Julian calendar standardized the solar year, providing a framework that remained in use for centuries. Microstory: a monk in a monastery adjusts the liturgical calendar to align with the solar year, ensuring that Easter and other feast days are observed correctly. Through careful observation, calculation, and adjustment, The religious calendar demonstrates the ongoing human endeavor to harmonize life with celestial rhythms. Later, the Gregorian reform corrected drift in the Julian calendar, illustrating humanity's continual pursuit of temporal accuracy. Even beyond the practical, calendars shaped cultural imagination. They became tools for storytelling, myth-making, and cosmic understanding. Societies encoded knowledge of planetary motion, seasonal changes, and historical events into their calendrical systems. Each adjustment, calculation, or prediction was an act of intellectual curiosity and cultural preservation. Microstory. In ancient China, scholars compile astronomical records into almanacs that instruct farmers, guide rituals, and preserve celestial knowledge. The almanacs become both practical guides and repositories of collective wisdom, connecting daily life to the cosmos. The story of calendars across civilizations reveals a pattern. Human societies, despite geographical separation, shared the same imperative: to organize time in ways that serve both practical and symbolic purposes. Observing the moon, sun, and stars, recording their patterns, and adjusting human schedules accordingly created continuity across generations. Knowledge traveled through trade, conquest, and scholarly exchange, resulting in calendars that reflected both local needs and universal principles. Reflecting on this long history, one sees that the human quest to structure time was driven by curiosity, necessity, and creativity. From Babylonian priests predicting eclipses to Mayan astronomers carving ceremonial stones. From Egyptian farmers following the Nile's rhythms to Chinese astronomers refining lunisolar calculations, societies developed tools to measure, interpret, and coordinate with the universe. These tools not only guided labor and ritual but nurtured collective reflection, philosophical inquiry, and cross-cultural exchange. Microstory. A Mayan astronomer, an Egyptian priest, and a Chinese scholar, though separated by oceans and centuries, share a fundamental human concern: understanding and organizing time to align human activity with cosmic order. Their work, though culturally distinct, illustrates a universal pursuit that continues to this day. Modern calendars, leap years, and astronomical predictions echo their efforts, showing that the rhythm of human life has always been in dialogue with the rhythm of the cosmos. The development of calendars also taught lessons in adaptation and resilience. Civilizations learned to reconcile observational discrepancies, adjust calculations, and refine instruments. These practices reinforced critical thinking, collaborative observation, and long-term planning. Calendars became both mirrors of cultural sophistication and engines of technological and social innovation, enabling societies to thrive despite environmental, astronomical, or political challenges. Even today, when we glance at a modern calendar app or check a digital planner, we are participating in a tradition that stretches back thousands of years. We are beneficiaries of millennia of careful observation, calculation, and cultural exchange. The rhythms of our work, our festivals, and our civic lives remain tied to the cosmic patterns first noted by ancient observers. Understanding calendars is more than knowing dates. It is recognizing the human capacity to measure, coordinate, and reflect upon the inexorable flow of time. As centuries passed, humanity's fascination with the passage of time deepened. Sundials and water clocks had provided a functional framework, calendars organized days and seasons, but the desire for precision and universality led inventors and artisans to explore new mechanisms. Timekeeping became not only a tool for survival or ritual, but a statement of ingenuity, artistry, and the human desire to measure the intangible with tangible tools. In medieval Europe, the first mechanical clocks began to emerge in the 13th century. Tower clocks, often installed in cathedrals or town halls, represented both technological innovation and civic pride. Unlike sundials, which relied on sunlight, these clocks could function in overcast weather or at night, and they provided audible signals bells that structured public life. Citizens in towns from Paris to Prague soon depended on these striking clocks to regulate daily activities, from market hours to curfews. Microstory. Imagine a monk in a cathedral in 1320, climbing the narrow spiral stairs to the tower, lantern in hand. He winds the clock, adjusts the gears, and ensures that each chime echoes across the town, signaling prayer times for the faithful. Every day, this ritual synchronizes the spiritual and practical life of the community. These early mechanical clocks relied on water-driven mechanisms and gears, translating fluid motion into the predictable movement of hands or chimes. The invention of the escapement, a mechanism that allowed gears to move forward in controlled increments, represented a breakthrough in accuracy and consistency. Each tick was a marvel of engineering, transforming human perception of time from approximate and natural into precise and standardized. Artisans devoted years to perfecting these devices, experimenting with weights, gear ratios, and materials. Microstory. A medieval artisan in Florence painstakingly assembles a tower clock, testing each gear and wheel. Townsfolk gather to watch, marveling at the precision of the mechanism. When the clock finally strikes, the artisan earns not only fame but the admiration of a city learning to live by mechanical rhythm. The Renaissance further accelerated the quest for precision. Spring-driven clocks allowed for portability, paving the way for personal timepieces. Miniaturization and craftsmanship turned watches into symbols of status, wealth, and sophistication. Wealthy merchants and nobility adorned themselves with intricate timepieces, demonstrating both taste and mastery of innovation. Microstory. A Venetian merchant opens a small case containing a delicate spring-driven watch, marveling at its miniature gears and engraved designs. With each winding, he participates in the centuries-long journey of human ingenuity that began with shadows and flowing water. Timekeeping technology reshaped societies. Markets opened and closed according to precise schedules, work shifted from natural rhythms to regimented hours, and travel could be coordinated over longer distances. The psychological impact of knowing exact time subtly altered human behavior, creating new expectations for punctuality, productivity, and social coordination. People began to measure their lives not only in seasons and days, but in hours, minutes, and eventually seconds, reflecting a deeper desire to harmonize personal and societal rhythms with cosmic order. Cross-continental exchange played a vital role in refining mechanical horology. Knowledge traveled through trade, scholarship, and conquest. European artisans drew inspiration from mathematical treatises and astronomical devices from the Islamic world, while innovations in clockmaking from China and Japan influenced gear design, escapements, and craftsmanship. Microstory. In a bustling port city, an engineer studies an intricate water-driven astronomical clock brought from the east. Inspired, he adapts the mechanism for a new tower in his hometown, blending foreign precision with local artistry. This cross-pollination illustrates that mechanical timekeeping, while technical, was deeply embedded in human networks of collaboration and curiosity. The precision of mechanical clocks allowed societies to push the boundaries of exploration and scientific understanding. Astronomers could track celestial movements with greater accuracy, navigators could estimate longitude, and mathematicians could perform experiments with exact timing. The development of mechanical clocks bridged the gap between observation and measurement, turning human curiosity into replicable and reliable knowledge. Microstory. An astronomer in 16th century Prague uses a tower clock to measure planetary transits. The careful observation enables predictions that are recorded and shared with scholars across Europe. Time, once abstract and natural, becomes a tool for discovery. Portable timepieces further democratized the concept of precision. Scholars, merchants, and travelers could carry time with them, coordinating meetings, trade, and research across cities and continents. The psychological transformation was profound. People now felt a continuous awareness of time, adjusting behavior according to seconds, not merely hours. Even leisure activities, such as music performance or ceremonial events, adapted to new expectations of synchronization. Each tick of a watch reflected centuries of accumulated ingenuity, a quiet testament to human aspiration. Craftsmanship intertwined with science and mathematics. Renaissance artisans combined geometry, metallurgy, and design to create mechanisms that were not only functional but aesthetically beautiful. Intricate engravings, gilded components, and innovative engineering reflected a culture that valued the union of knowledge and art. Microstory. A Florentine artisan spends months constructing a gilded clock with painted zodiac signs, testing each gear meticulously. When completed, the clock is displayed in the city square, admired by scholars, merchants, and citizens alike. It serves both as a tool and a cultural emblem, reminding the city of the harmony between human ingenuity and cosmic rhythm. The spread of mechanical clocks also spurred philosophical reflection. People became increasingly aware of their lives in measured increments. Literature and art began referencing time more explicitly, portraying fleeting moments, the inevitability of aging, and the relationship between human action and the cosmos. Timekeeping was no longer just a practical matter. It was a lens through which to understand existence. Each clock ticked not only hours but also the subtle pulse of human consciousness, marking both practical and existential progress. By the 17th century, innovations continued with the introduction of pendulum clocks by Christian Huygens, dramatically improving accuracy. These innovations laid the groundwork for modern horology, demonstrating the iterative nature of human ingenuity. Observation, experimentation, and refinement over centuries produced instruments capable of synchronizing communities, nations, and eventually the world. Microstory. A Dutch scientist carefully adjusts a pendulum, observing how the swing reduces timing errors. He records the result in a journal, confident that this refinement will influence not only local timekeeping but astronomical observation across Europe. Cross-cultural influence remained vital. Instruments, designs, and techniques flowed between Europe, the Middle East, and East Asia, enriching local innovation. Knowledge exchange was not always smooth. Sometimes ideas were misunderstood or adapted in unexpected ways, but the cumulative effect was profound. By connecting different approaches to measurement, civilizations expanded both precision and imagination. Mechanical clocks became more than tools. They were symbols of shared human curiosity, ingenuity, and ambition. Timekeeping's societal impact grew as commerce expanded. Precise schedules allowed for complex trade networks, coordinated transport, and financial transactions that demanded reliability. Microstory. In Venice, a merchant coordinates shipment arrivals using mechanical clocks in multiple warehouses. Each chime signals departure or arrival, preventing costly errors and demonstrating how precision timekeeping directly influenced economic growth. Across continents, Time became not only a scientific concern but a pillar of social organization and commerce. Even in private life, watches and portable clocks transformed human experience. Individuals could measure personal productivity, coordinate social engagements, and synchronize tasks. Miniaturized timepieces brought control over daily routines, instilling discipline and a subtle awareness of mortality. Each winding of a watch was a small act of mastery over the abstract, linking human effort to the inexorable march of time. Ultimately, the development of mechanical clocks reflects the marriage of human observation, ingenuity, and cultural aspiration. From water-driven gears in a cathedral tower to delicate watches on a Renaissance noble's wrist, mechanical timekeeping illustrates humanity's desire to impose order, understand the cosmos, and coordinate complex societies. Each innovation built upon centuries of knowledge, connecting ancient observation with modern precision, and reminding us that the quest to measure time is both practical and deeply human. The journey of mechanical horology also serves as a metaphor for human persistence. Trial and error, creativity, and collaboration are as essential as technical skill. Observing shadows, dripping water, or celestial alignments is transformed into moving gears, escapements, and pendulums. Societies learn to rely on these instruments not merely for practicality but for shared understanding, community coordination, and philosophical reflection. Time became something humans could measure, share, and ultimately respect. Microstory. Across Europe, an artisan, a scholar, and a merchant each interact with a different clock. The artisan perfects the mechanism, the scholar uses it to map the stars, and the merchant relies on its chimes to regulate commerce. Though their goals differ, they are united by the pursuit of precision, illustrating that the mechanical measurement of time is a collaborative achievement that transcends disciplines and geographies. Long before GPS satellites or atomic clocks, humanity faced a profound challenge: how to navigate vast oceans, explore distant lands, and map the heavens with confidence. Timekeeping had evolved from sundials and water clocks to intricate mechanical marvels, but the demands of astronomy and navigation required an entirely new level of precision. Observatories, maritime innovations, and the systematic sharing of knowledge across continents transformed human understanding of time from a local measurement into a global framework. In Europe, from the 16th century onward, astronomical observatories became centers of both scientific inquiry and civic pride. Scholars meticulously mapped the positions of stars, planets, and comets, striving to create accurate celestial charts. These charts were not mere curiosities. They were essential for navigation, calendar reform, and the emerging field of physics. Microstory. In Prague, an astronomer carefully notes the transit of Venus across the Sun, calculating the planet's position relative to known stars. His observations are recorded in painstaking detail, shared with colleagues in distant cities, and contribute to a growing network of knowledge that spans Europe. Observatories in China, meanwhile, documented eclipses, planetary conjunctions, and comet appearances with equal rigor. Ancient texts from the Middle East describe observatories where scholars combined mathematical models with empirical observation, ensuring that each celestial event was carefully timed and recorded. Lunar and solar observations became crucial not only for calendars but for long-distance navigation, allowing sailors to chart positions by night and by day. Maritime navigation posed one of the greatest tests of precise timekeeping. While latitude could be determined with relative ease using the angle of the sun or stars, longitude remained elusive. Ships would lose track of their east-west position, sometimes drifting hundreds of miles off course. The consequences were catastrophic. Lives were lost, cargo spoiled, and trade disrupted. The solution demanded a combination of ingenuity, perseverance, and technological sophistication. John Harrison, an English carpenter and self-taught horologist, tackled this problem in the 18th century with a relentless focus on precision. Microstory: Harrison's marine chronometer, a compact and remarkably accurate sea clock, is tested on a voyage across the Atlantic. A sailor keeps constant watch over the instrument, noting every tick against celestial observations. The moment comes to determine longitude at sea, and the chronometer provides a reading precise enough to save lives and protect cargo. The success of Harrison's invention revolutionized navigation, transforming oceans from perilous mysteries into traversable highways of commerce and exploration. The implications of accurate time extended far beyond maritime safety. Coordinated observations of eclipses, planetary motion, and celestial transits became possible, enabling scientific breakthroughs in physics and astronomy. Scholars could now compare measurements across continents, confident that their observations were synchronized. Microstory: An astronomer in Beijing records the timing of a solar eclipse while corresponding with colleagues in India and Europe. Together, they triangulate observations, refining models of celestial motion. These coordinated efforts exemplify the growing recognition that precision in timekeeping was essential not just for practical survival, but for expanding human understanding of the universe. Calendars, too, benefited from this new precision. Accurate clocks allowed astronomers and scholars to predict celestial events years in advance, facilitating agricultural planning, religious ceremonies, and civic organization. In Europe, the adoption of the Gregorian calendar relied on improved astronomical observations, correcting the drift inherent in previous systems. Microstory: A monk in a remote abbey consults both a mechanical clock and astronomical charts to determine the correct date of Easter. His meticulous calculation ensures that the festival aligns with celestial cycles, illustrating the intimate connection between measurement, ritual, and community life. As navigation and astronomy advanced, so too did the dissemination of knowledge. Trade networks, colonial expansion, and scientific societies facilitated the global exchange of instruments, methods, and observations. Maritime charts, astronomical tables, and clock designs moved from ports to cities, from universities to observatories, and from one scholar's hands to another. Cultural and technological connections became critical. Ideas borrowed from one civilization were adapted, improved, and integrated into others, creating a web of knowledge that spanned oceans and continents. Microstory: In Lisbon, a navigator examines a set of star charts imported from Venice, cross-referencing them with a local chronometer. The combination allows him to plot a course to the Indian Ocean with unprecedented accuracy, demonstrating the power of knowledge transfer in shaping exploration and commerce. The psychological impact of synchronized, precise time on sailors, merchants, and scholars was profound. Humanity could now exert some measure of control over the chaotic natural world. While earlier societies had observed patterns and rhythms, the ability to measure time precisely enabled prediction and planning on a global scale. Voyages became less perilous, trade more reliable, and scientific investigation more rigorous. Individuals felt a new confidence in their capacity to navigate both seas and stars, understanding that human ingenuity could extend reach and knowledge beyond local horizons. The integration of clocks and calendars into navigation also catalyzed economic and cultural expansion. Ports became hubs of innovation, merchants relied on timing to schedule arrivals and departures, and coastal cities thrived on the reliability of coordinated commerce. Microstory: In Amsterdam, A trading company relies on synchronized chronometers to ensure that ships carrying spices from Asia dock at the correct time for unloading. The precision of mechanical timekeeping enables the city to flourish economically while reducing the risk of loss or delay. Time, once a local and abstract notion, becomes a shared global resource, structuring human activity on a scale previously unimaginable. The pursuit of precise time also influenced exploration and discovery. Mariners ventured into uncharted waters with a confidence grounded in accurate clocks and charts. Microstory: a sailor navigating treacherous waters off the coast of South America uses a newly minted chronometer to calculate longitude, avoiding reefs and shoals that had claimed previous ships. The chronometer, a culmination of centuries of mechanical innovation, transforms risk into knowledge, demonstrating how precise measurement empowers human agency. The tools of timekeeping thus become instruments of liberation, allowing humanity to traverse, document, and connect the globe. Simultaneously, astronomy flourished as a science. Observatories became centers of experimentation, education, and international collaboration. Scholars shared methods for timing transits, eclipses, and lunar cycles, establishing standards that allowed distant observations to be meaningfully compared. Microstory: a French astronomer collaborates with counterparts in Cairo and Beijing, coordinating the timing of planetary observations to refine models of motion and predict eclipses. The results not only advance theoretical knowledge but also enhance practical applications such as navigation and calendar reform. The global synchronization of time illustrates the iterative nature of human ingenuity. Each technological breakthrough, from tower clocks to pendulums to marine chronometers, built upon centuries of observation, experimentation, and cultural exchange. Communities learned from each other, adapting innovations to local conditions while refining techniques for broader applications. The cumulative impact reshaped not only daily life but the very scope of human ambition, enabling exploration, commerce, and science on an unprecedented scale. Even everyday life felt the reverberations of this evolution. Markets, festivals, religious ceremonies, and civic events increasingly relied on precise timing. Microstory: in Edo period Japan, a city official consults a mechanical clock imported from Europe, using it to schedule a market and coordinate water management projects. Across the Pacific, a Spanish galleon relies on coordinated chronometers to reach the Philippines at the right season for trade. The human experience of time becomes simultaneously local and global, structured yet flexible, precise yet interconnected. Ultimately, astronomy, navigation, and global synchronization of time highlight a recurring theme: humanity's relentless pursuit of understanding, organizing, and mastering temporal and spatial dimensions. The desire to measure time accurately transcended practical necessity, fostering scientific inquiry, technological innovation, and cultural exchange. The tools developed for this purpose, from observatories to chronometers, reflect both technical skill and human imagination, bridging centuries and continents in the pursuit of knowledge. Microstory: across Europe, Asia, and the Americas, sailors, astronomers, and scholars each rely on precise instruments to guide their work. Whether charting a course, predicting an eclipse, or coordinating civic events, they participate in a shared human endeavor: the synchronization of society, science, and the cosmos. Each clock tick, each careful observation, contributes to a collective understanding that transforms the world from a series of isolated communities into an interconnected web of knowledge and exploration. The synchronization of time, once a lofty intellectual pursuit, became a practical necessity for global civilization. Precise timekeeping allowed humans to navigate treacherous seas, coordinate economic networks, and pursue scientific discovery with unprecedented reliability. Observatories, chronometers, and coordinated observations illustrate the marriage of meticulous measurement with human curiosity, ambition, and courage. The result is a world in which temporal precision is a shared infrastructure, underpinning exploration, commerce, and the spread of knowledge across continents. From the shadow clocks of ancient Egypt to the intricate gears of Renaissance tower clocks, humanity's journey to measure time had always been one of innovation, curiosity, and persistence. Yet, as the 20th century dawned, a new frontier appeared: the microscopic world of atoms and the promise of near-perfect precision. Atomic clocks would not only redefine what it means to measure a second, but also anchor the global synchronization of modern life, transforming science, technology, and daily human activity in profound ways. The pursuit of atomic time emerged from the realization that mechanical and even pendulum-based clocks, though extraordinarily accurate for their eras, were limited by physical constraints. Gears, escapements, and pendulums were subject to friction, temperature variation, and material fatigue. Scientists sought a method rooted in nature's own constants. Microstory. Imagine a team of physicists in the 1950s carefully calibrating the first cesium atomic clock in a dimly lit laboratory. The room hums with machinery, oscillators, and the quiet intensity of minds at work. They observe the vibrations of cesium atoms, counting each oscillation, and realize that these natural vibrations provide a standard far more stable than any mechanical device. It is a moment of revelation, a leap in precision that would ripple across disciplines and continents. Cesium and hydrogen maser clocks soon became the backbone of atomic timekeeping. Each cesium atom oscillates at a frequency that defines a second with extraordinary consistency. Microstory. At a research facility, scientists carefully shield their instruments from temperature fluctuations and magnetic interference, calibrating the cesium standard with painstaking accuracy. Each adjustment is documented meticulously, a small yet monumental step in humanity's quest to tame time itself. By defining the second based on atomic vibrations, researchers created a measurement that was universally replicable, independent of location, weather, or human error. Atomic clocks did more than redefine seconds. They became the foundation for global synchronization. Time zones, once based on local solar observation, were now coordinated with unprecedented precision. International atomic time and coordinated universal time emerged, ensuring that clocks from Tokyo to New York ticked in harmony. Microstory. In Geneva, a technician oversees the synchronization of multiple atomic clocks from around the world, comparing oscillations transmitted via satellites and fiber optic networks. The work is invisible to most, yet it underpins air travel, financial markets, and telecommunications, silently orchestrating the rhythm of modern civilization. Perhaps the most transformative application of precise atomic timing is GPS. Global positioning systems rely on satellites with atomic clocks to determine exact locations on Earth. A sailor in the North Atlantic checks a GPS receiver, relying on the synchronization of multiple orbiting satellites. Each signal is calculated down to the nanosecond, guiding vessels safely through treacherous waters. The marvel is that this technology, which traces its lineage back to ancient astronomers and mechanical horologists, now supports navigation for both professionals and everyday citizens. The same atomic precision that once guided observatories now directs cars, smartphones, and airplanes with breathtaking accuracy. Telecommunications and digital networks also rely on synchronized time. High-speed financial trading, internet infrastructure, and global communications would falter without precisely coordinated timestamps. In a data center, engineers monitor servers that must synchronize within microseconds. A misaligned clock could result in missed trades, misrouted data, or communication failures. The invisible work of atomic timekeeping becomes the pulse of modern society, regulating transactions, information flow, and even social interactions in ways most of us never see but always depend upon. Yet beyond the technical marvels, atomic timekeeping reflects a deeply human story. Researchers, engineers, and scientists continue to marvel at the universe's constancy, finding awe in counting oscillations of a single atom and using that knowledge to structure the lives of billions. A young physicist gazes at the cesium beam apparatus, reflecting on the centuries of observation that led here, from sundials to mechanical clocks, maritime chronometers to atomic oscillators. She feels a profound connection to generations of thinkers who sought to harmonize human activity with the cosmos. Everyday life now depends on these precise measurements. Flights depart and land according to coordinated atomic time. Financial markets operate across continents, trusting synchronized clocks to execute transactions with staggering speed. Mobile networks, streaming platforms, and GPS-guided vehicles all rely on the same invisible rhythm. Humanity, once constrained by local sunrises and seasonal cycles, now exists in a globally coordinated temporal framework. The evolution of timekeeping also invites reflection on mortality, productivity, and philosophical understanding. Once, humans marked life in days and seasons, tethered to observable natural events. Mechanical clocks introduced hours, minutes, and seconds, creating a disciplined society attuned to punctuality and coordination. Atomic clocks and digital synchronization extend this consciousness, measuring intervals smaller than the blink of an eye. A philosopher contemplates how our ancestors aligned life with cosmic rhythms, how medieval townsfolk adjusted labor to bell chimes, and now how a single nanosecond can guide a spacecraft or stabilize a financial market. The scale may have changed, but the underlying human fascination with mastering and understanding time persists. As with previous eras, human creativity and collaboration remain central. Atomic time did not emerge from a single mind but from networks of scientists building on centuries of accumulated knowledge. Techniques developed for observatories informed laboratory designs. Lessons from mechanical engineering guided instrument construction. International cooperation ensured synchronization across borders. Time, while measured with atomic precision, is also a testament to the social, cultural, and intellectual networks that span the globe. The philosophical dimension is equally profound. From observing shadows and dripping water to counting atom oscillations, humans have always sought to harmonize with the universe, to impose structure on the ephemeral. Each advancement reflects not only technical skill but also cultural values. Curiosity, diligence, collaboration, and the desire to connect generations. Microstory. In a quiet lab, a technician observes an atomic transition and reflects on how humanity has evolved from marking time with stones and shadows to manipulating the fundamental vibrations of matter itself. It is both humbling and inspiring, a reminder that the quest to measure time is inseparable from the story of human aspiration. Modern atomic clocks also underscore our responsibility to preserve and transmit temporal knowledge. Digital synchronization may appear abstract, yet every failure server outages, GPS misalignments, or lost data packets reminds us of time's fragility. A team works frantically to recalibrate atomic clocks after a technical glitch threatens satellite synchronization. The consequences ripple across transportation, communication, and commerce. Maintaining precision is not merely technical. It is a moral and societal duty, reflecting centuries of human investment in understanding and managing time. Beyond their practical applications, atomic clocks inspire wonder and imagination. Knowing the universe's heartbeat at the atomic level connects humanity to a broader cosmic rhythm. The transition from sundials to atomic oscillations is more than technological evolution. It is a story of human curiosity and the relentless drive to align life with the fundamental structure of reality. A high school student peers into a laboratory demonstration of a hydrogen maser, marveling at the invisible oscillations that define the modern second. She senses continuity with monks, astronomers, and artisans across millennia, all engaged in the same pursuit, capturing the essence of time. Atomic precision has also transformed scientific inquiry. Experiments in quantum mechanics, astronomy, and space travel rely on synchronized time to unprecedented degrees. Large-scale projects like the International Space Station, intercontinental particle accelerators, and global climate monitoring all depend on atomic clocks. The instruments connect local labs to international networks, ensuring that observations are comparable, experiments reproducible, and knowledge cumulative. Humanity's mastery of time, once local and imprecise, now supports endeavors on a planetary and interstellar scale. Reflecting on this journey invites a profound question. If humans have pursued ever greater precision in measuring time, what is the next frontier? Consider standing beside a physicist adjusting an optical lattice clock that measures time to within a quintillionth of a second. The achievement is staggering, yet it is also part of a continuum stretching back to sundials, water clocks, and mechanical towers. Each innovation builds on previous ingenuity, each tick a reminder of our persistent quest to understand, harmonize, and coordinate with the cosmos. The story of atomic time culminates in both awe and responsibility. These instruments touch nearly every aspect of modern life, yet they are also reminders of human ingenuity, collaboration, and cultural continuity. From measuring shadows to vibrations of cesium atoms, humanity has demonstrated a remarkable capacity to invent, observe, and refine. A family books a flight, unaware that their schedule, the GPS guiding the plane, and the digital transactions securing tickets all depend on atomic clocks ticking in silent, precise harmony. The ordinary becomes extraordinary when seen through the lens of temporal synchronization. Finally, the story invites reflection and engagement. Imagine traveling through the history of time measurement. Which era would you choose to witness? Standing beside a Babylonian priest, a Renaissance artisan, or a 20th century atomic physicist? Each moment reflects the same human impulse: to observe, record, and harmonize with the universe. Atomic clocks, GPS, and digital timekeeping represent the culmination of this quest, connecting civilizations across millennia and continents, while reminding us that time is both measured and lived, structured and experienced, precise and profoundly human. If you could witness one moment in humanity's long journey to measure time, which era would you choose, and why? Share your thoughts below and continue the conversation about how time shapes our lives.